One of the most remarkable characteristics of the human body is its ability to control its internal environment, no matter what the conditions are like outside. Whether you're sweating profusely in a sauna or doing strenuous exercise in the hills, the body makes the adjustments necessary to ensure that all its cells are kept in a constant or steady state. So what mechanisms are used to regulate body conditions?
Essentially, all the organs and tissues of the body are involved in maintaining the internal environment, a process known as homeostasis. It's the subject of this episode of The Virtual Body. Planet Earth is unique in our solar system. It regulates itself to keep any changes within a narrow margin. By doing this, it maintains what's known as a steady state, its own form of homeostasis.
Here in this greenhouse, it's important for the development of these plants that their environment remains more or less constant. Too hot or too cold and the plants die, and that's bad for business. The temperature of the greenhouse is regulated with sensors and thermostats. If the greenhouse gets too cold, the thermostat senses this, activates the heating and closes the ventilation. When the temperature gets too hot, the heating is switched off and the ventilation opens. A similar set of controls work with light intensity. When it's too sunny, the shades are brought across. When the sun goes in, the shades are removed. These light and temperature regulations are examples of negative feedback. That is, when a change away from the ideal triggers a reaction designed to bring conditions back to normal. This principle of detection and response is fundamental for control in lots of areas of life, such as in the supermarket. As the shoppers leave the supermarket, the checkout tells a computer in the warehouse that these items need replacing.
To begin investigating how our body controls its physiology, it's worth asking several questions. Firstly, what factors bring about change? Secondly, how are these changes detected and, if necessary, reversed? And lastly, what happens if these changes are not detected?
Whenever the body experiences a change, whether internally or externally, the change is detected and an appropriate response occurs. Why do conditions in the body need to remain constant? Well, to answer this question, let's look at what would happen if just 3 typical processes were not regulated. To start with, let's examine the water content of the body. We all need water. Our cells are bathed in a watery solution, but what would happen if that water content were not controlled at a cellular level? All our cells contain cytoplasm, a complex solution that is separated from its surroundings by a semi-permeable cell membrane. All cells can gain and lose water by osmosis. If the concentration of water in the solution outside the cell becomes much higher than inside, then water will pour in through its membrane. Animal cells are unable to bail out this excess water and the cell ruptures. Now let's examine what happens when a cell is exposed to too much heat. If the body's temperature is increased, heat-sensitive cells detect this change. The capillaries dilate, resulting in a greatly increased blood flow to the skin. This is termed vasodilation, and heat is thus lost to the environment. Zooming into an individual cell, what happens when the temperature increases? All cells are made of proteins, such as enzymes. Above 40 degrees centigrade, enzymes are denatured. That means they cannot be reformed. Cell activity grinds to a halt and it dies.
Just a tad.
And finally, sugar concentration. Too much sugar in water is drawn out of the cell, causing it to collapse. So the body carefully regulates sugar levels by the release of hormones such as insulin and by the activation of enzymes.
So let's look at temperature regulation within the body first. A sauna is an incredibly hot environment, and this young man looks very hot and sweaty. Humans, like all mammals, are a warm-blooded species. We refer to them as homeothermic. We can control our own body temperature to a certain extent at around 37 degrees centigrade, despite changes in the temperature of our surroundings or indeed from the heat we generate for ourselves through exercise or internal chemical reactions. So what happens when we sit in a sauna or sunbathe on a tropical beach? Our ability to thermoregulate, to regulate temperature that is, happens both through our own voluntary actions and through the automatic mechanisms of the body. Changes in external temperature are detected here by temperature sensors in the skin. We sense the change in temperature and feel hot or cold, and so we can take appropriate action. Most of the time, however, we're unaware of thermoregulation taking place. It happens automatically, primarily by the brain taking control of the regulation. One part of the brain is responsible for detecting most of the changes that can affect us. This is the hypothalamus. It works in conjunction with the body's master gland, the pituitary. Together, they form the main control function in homeostasis.
In the sauna, the temperature is rising. High temperatures affect the rate of chemical reactions in cells and can even threaten their very structure by destroying the proteins in the cell membrane. Think about how different cooked egg is from raw. The body must prevent its insides becoming as hot as the outside.
Remember, the hypothalamus is like the body's own thermostat. It measures the temperature of the blood flowing through it. If the temperature goes up, the hypothalamus initiates a corrective response, sweating. The sweat glands work overtime, producing lots of sweat, which evaporates, cooling the skin, together with the blood flowing through it.
Some responses to temperature change are clearly visible to the eye. If our man from the sauna now takes an extremely cold shower, he shivers. This rapid contraction of his muscles generates heat. The covering of hair over our bodies also helps with temperature control.
Our hairs stand on end, a process known as piloerection. In this way, hairy mammals trap a layer of air above the surface of the skin, forming an insulator and preventing heat loss. Because we humans don't have much hair on our skin, the most obvious result is that we get goose pimples. But corrective responses also take place beneath the surface of the skin.
When the body needs to reduce its heat loss, these blood vessels narrow, a process called vasoconstriction. Warm blood is kept deep within the body so that heat loss to the outside is minimised. This is why the skin can look blue in the cold.
However, there is a limit to how much heat variation our body can control. Let's put it to the test under some severe weather conditions.
A wild, wet and extremely cold day in the hills.
We've had reports of 2 people huddled together on the gliders. Set off yesterday to walk over the gliders and I think down the Griffin. We can get the vehicle packed and get down there. But I would suspect with the weather last night and the rain and everything, cold, wet, and I think rather fed up.
These extreme weather conditions can be very dangerous for people who go out to enjoy the countryside without proper knowledge and equipment.
Also backed up by a phone call from a husband who says that they were supposed to camp somewhere down in Capel last night and be home sometime today and didn't make a sort of early morning phone call to say that everything was hunky-dory. Clive will look after the medical side of it, Mike can look after the mechanics. Okay.
Hiya, hiya. Marion, we're going to look after Anna. I want you to come with us now. Okay? Okay, she's not breathing as fast as I would want. You can have the oxygen. Let's have a listen at her heart. Her pulses are absent at the periphery. Capillary refills delayed. Hello, Anna. Can you hear me? I get a little bit of a response to voice. Respiratory rate's only 8, heart rate's only 50.
If the core temperature of the body falls below 35 degrees centigrade, much of the body's chemical activity slows down and hypothermia may begin. By the time the core temperature has fallen to 29 degrees centigrade, the ability of the hypothalamus to regulate temperature is completely lost. The body will start to cool until eventually it would match the external temperature. The mountain rescue team was successful in saving the hill walkers this time, but if the body's core temperature drops to 25 degrees centigrade or below, death is likely to occur.
Well, with our mother and daughter safely down from the mountain, let's now take a look at another physiological state controlled by homeostasis, the concentration of sugar in the blood. Blood glucose is important for the correct function of body cells. It's required for cell respiration. There's a narrow range between 80 and 90 milligrams per 100 cubic centimetres of blood glucose that's ideal for the body. When we eat a lot of certain foods, like simple carbohydrates, then blood glucose rises. Negative feedback sets in, and blood glucose is returned to normal within about 2 hours. The reverse occurs if the blood glucose level falls too low. So how does the body regulate blood glucose in this way? This is the pancreas. It has receptors that detect the rise in blood glucose. The pancreas then releases insulin into the blood.
Insulin is a hormone which is released in response to rising blood sugar levels. It travels in the bloodstream to all tissues, particularly the liver and muscles, where it sets about removing the sugar from the blood. It does this in 2 ways, by converting glucose to glycogen in the liver and by promoting the uptake of glucose by muscles for cell respiration. As a result, glucose leaves the bloodstream and the blood glucose level falls.
What happens if the blood glucose levels fall too far? Well, the pancreas receptors detect the fall in blood glucose and another hormone is released called glucagon. Its job is to increase the amount of glucose in the blood.
It activates enzymes inside the tissues, especially the liver and muscles, which then converts the glycogen back to glucose. The glucose passes out of the tissue and into the bloodstream. Alcohol has a big effect on homeostasis. It interferes with both temperature control and water regulation. When you drink, the alcohol level in the blood increases. It begins to interfere with brain activity and the mechanisms that control your water and temperature regulation. And you become easily dehydrated and don't respond properly to heat and cold.
The maintenance of water content is the last homeostatic mechanism we're going to examine. The regulation of water content takes place in the kidneys and is under the control of a hormone called ADH, antidiuretic hormone. Like most homeostatic mechanisms, the maintenance of water balance involves negative feedback. What happens when the body is short of water? The concentration of salts in the blood becomes high. This high concentration is detected by special cells called osmoreceptor cells, found in the hypothalamus. The hypothalamus responds in 2 ways. Firstly, it stimulates the thirst centres in the brain. And secondly, it stimulates the pituitary gland to secrete antidiuretic hormone, ADH, into the blood, where it's carried to the kidneys. It's the kidney's job to filter the blood and regulate its water content. Our urinary system is contained in our abdomen. But how is urine produced? Well, urine is a watery fluid that's produced in the kidneys. It's our body's way of removing soluble toxins that have accumulated from our chemical processes. The body needs to remove them because if they were allowed to build up, they would poison the tissues. The urine trickles down the ureters, or tubes connecting the kidneys to the bladder. As more urine collects, the bladder expands, and at a certain point it's automatically emptied. Luckily, we can learn to override the automatic emptying process. We empty the bladder by the process